It is late and you have arrived here. Whether your day was kind or difficult, this hour is yours to rest. Let the small worries that climb into the dark slip back beneath the surface. Tonight we will drift very slowly into one of the deepest and quietest questions our species has ever asked. A question so simple that a physicist once posed it over lunch, and so vast that we have not finished answering it in the 70 years since. Where is everyone? This is the Circadian Institute. We exist for the long nights, for the in-between hours when the body is ready to sleep, but the mind is still moving. Tonight, our subject is the deep, slow story of the Fermi paradox, the strange silence of a universe filled with countless stars and uncounted worlds. The question of why, after billions of years of cosmic time, we have not heard from anyone, the patient hypotheses that try to explain that silence, the long, careful searches we have made, the dark possibilities, the gentle possibilities, and the quiet meaning our cosmic loneliness might have for our own small civilization on a small blue planet at the edge of an ordinary galaxy. If this kind of slow journey suits you, subscribing keeps these nights arriving. Tonight we will travel together through one of the strangest and most beautiful puzzles in modern science. We will consider the question of where everyone is, why the universe seems so empty of voices when, by every reasonable calculation, it should be full of them. We will sit with that silence patiently, the way we might sit with the dark sky above a quiet field. There is no hurry. We have all the time we need. To begin tonight's journey, we will visit a single question. It is a simple question that has shaped much of modern thinking about life in the universe. The question is this: in a cosmos with billions of stars, many of them older than our own sun, where many of those stars must have planets, and where many of those planets must have conditions suitable for life, why have we never seen any sign of another civilization? Where is everyone? The question is so simple that a child could ask it, looking up at the night sky and wondering whether anyone is looking back. And yet the question is so deep that physicists, astronomers, biologists, and philosophers have been working on it for more than 70 years. No clear answer has been found. Many possible answers have been proposed. The mystery itself has only grown larger as our telescopes have grown more powerful. Our own galaxy, the Milky Way, contains roughly 200 to 400 billion stars. The observable universe contains around 2 trillion galaxies. The total number of stars in the cosmos is so large that human minds cannot truly hold it. There are more stars than there are grains of sand on every beach on Earth combined. The numbers themselves should make the universe seem crowded with possibility. And yet, when we look out, we see only silence. No radio messages, no flashes of laser light, no giant engineered structures, no probes drifting past our solar system, no friendly visitors, no hostile visitors, no ruins of fallen empires, no artifacts left behind. The cosmic radio dials we have tuned remain quiet. The faint scatter of starlight reaching our telescopes shows no clear sign that anyone is out there. This contradiction between the apparent richness of the universe and the apparent silence we observe is the heart of the Fermi paradox. It is named after the physicist Enrico Fermi, who asked the question casually one day at lunch with colleagues. The mood of the question was almost light. but its implications were enormous, and they have grown larger as we have come to understand the universe more deeply. The paradox is sometimes stated more sharply. The Milky Way is roughly 13 billion years old. Even if interstellar travel is extremely slow, a single civilization that began spreading from star to star could cross the entire galaxy in a few tens of millions of years. Yet we see no evidence of any such civilization in our galaxy or beyond. The galaxy looks pristine, untouched, as if no one has yet arrived. There are two general categories of answer to the Fermi question. The first category says there really is no one else out there, or hardly anyone for some reason. The second category says there are others out there, but for some reason we do not see them. Within each of these categories, many specific hypotheses have been proposed. Tonight we will visit many of them in turn, gently, one by one. The question matters not only because it touches on the existence of other minds. It matters because the answer, whatever it turns out to be, has implications for our own future. If civilizations are rare because they tend to destroy themselves, then we should be careful. If they are rare because the steps that produced us were extremely improbable, then we are precious. If they are common but quiet, then our cosmic loneliness is only an illusion of perception. The question is also one of the few places where physics and biology and philosophy meet directly. To answer where everyone is, we have to estimate how often life arises, how often it becomes intelligent, how often intelligence builds technology, how often technology becomes detectable, and how long civilizations last. Each of these is its own deep question. Together, they form a chain of uncertainty stretching from quiet chemistry to the long fate of minds. Throughout most of history, the question would have had no real meaning. Our ancestors did not know how many stars existed, or that the stars were suns, or that other planets might orbit them. The cosmos seemed sufficiently inhabited by gods and spirits only in the last few centuries, as we mapped the scale of the universe and the time scale of life, did the question take its modern form. Even within the last 100 years, our understanding has shifted enormously. We now know that planets are common around other stars. We know that the basic ingredients of life, water, carbon, energy, are common in the cosmos. We know that life on Earth appeared remarkably quickly, almost as soon as the planet cooled enough to permit it. Each of these facts increases, not decreases, our puzzlement at the silence. Our telescopes have grown patient and sharp. We can detect planets 1,000 light years away. We can measure their atmospheres. We can listen to entire patches of sky for any radio whisper that might carry a signal. We have done these things carefully for decades, and the result so far has been silence, not the silence of an empty sky, but the silence of a sky we cannot yet read. It is important to acknowledge what the silence does not prove. It does not prove that no one is there. It only proves that, with our current tools and current attention, we have not yet detected anyone. Absence of evidence is not evidence of absence. The cosmic ocean is vast, and we have so far dipped only a small cup into it. What we have found in that cup tells us much, but it does not tell us everything. Still, the silence we hear is meaningful. It rules out some possibilities, it makes others more likely, and it leaves a strange, gentle, patient mystery hanging over our small civilization, a mystery that, depending on how we answer it, could matter enormously for the future we build. Tonight, we will sit with that mystery without rushing toward any conclusion. Now, gently, we will move closer to the moment the question was first formally asked. A quiet lunch at Los Alamos in 1950, where a physicist named Enrico Fermi gave the puzzle its name and its first careful formulation. Enrico Fermi was one of the great physicists of the 20th century. Born in Italy in 1901, he made fundamental contributions to nuclear physics, quantum mechanics, particle physics, and statistical mechanics. He led the first controlled nuclear chain reaction in 1942. He was awarded the Nobel Prize. He spent the latter part of his career at the University of Chicago and at Los Alamos National Laboratory in New Mexico. In the summer of 1950, Fermi was having lunch with 3 colleagues in Los Alamos. They were walking and talking about reports of unidentified flying objects and discussing whether interstellar travel might be possible. Fermi was a famous calculator. He would estimate quickly in his head whether numbers worked out. The conversation drifted from one cosmic topic to another, the way conversations often do at lunch. Then, in the middle of an unrelated comment, Fermi said simply, "Where is everybody?" It was such an offhand remark that his colleagues remembered it differently in later years, but the meaning was clear. Fermi was pointing out a strange contradiction. The galaxy is old. Other civilizations should have arisen. They should have had time to explore and to spread. Where are they? Fermi was not the first person to raise the question. Russian rocket pioneer Konstantin Tsiolkovsky had pondered something similar earlier. So had others. But Fermi's question gave the puzzle its memorable form, its sense of bewildered urgency, and the name by which it has been known ever since. The Fermi paradox was born in that quiet moment of cosmic puzzlement. The logic Fermi used was simple. He estimated the age of the galaxy. He estimated reasonable speeds of interstellar travel. He estimated reasonable rates at which a spacefaring civilization might colonize new stars. He multiplied. The result was that even a single technological civilization, starting tens of millions of years ago, should by now have spread throughout the entire galaxy, visiting every star, including ours. So either no such civilization existed, or it existed but disappeared, or it existed but chose not to expand, or it existed and expanded but for some reason left no trace we can detect. Each possibility had implications. None was obviously true. None was obviously false. The question simply hung there, waiting to be taken up by anyone who cared to think carefully about it. After Fermi's casual remark, the question stayed alive among physicists and astronomers, although it was not formally studied for some time. Over the next decades, as space exploration began, as radio astronomy matured, as our understanding of life and planets deepened, the question grew sharper. Each new piece of cosmic knowledge made the silence harder to explain. The discovery, decades later, that planets orbit most stars made the paradox more pointed. There were now known to be plenty of places for life to develop. The discovery that even Mars and the icy moons of Jupiter and Saturn might harbor microbial life made the basic ingredients seem common. With more places and more time, the silence became stranger, not less strange. In 1975, the astronomer Michael Hart wrote a careful paper arguing that the Fermi paradox was a serious challenge to the assumption that intelligent life is common in the universe. Hart calculated that if any nearby intelligent civilization existed and traveled at even modest speeds, they would have reached Earth by now. Since they have not, perhaps they do not exist. Hart's argument prompted decades of further debate. Other physicists offered counter-arguments. Frank Tipler took Hart's reasoning further and argued that self-replicating probes could explore the galaxy on even shorter timescales. Carl Sagan, by contrast, suggested that the galaxy might be quietly full of civilizations practicing restraint. The conversation grew. Today, the Fermi paradox is considered one of the great unsolved problems at the intersection of astronomy, biology, and philosophy. It is taught in universities, debated in scientific journals, and explored in popular books. The fact that it remains unsolved after 70 years is itself a kind of clue. The question is genuinely hard, and the universe is patient enough not to give us the answer easily. Fermi himself died in 1954, just 4 years after asking the question. He did not live to see the explosion of related scientific work, the discovery of exoplanets, the development of SETI, or the modern debates about the Great Filter and the Dark Forest. He left only the simple, devastating question, and the obligation for everyone who comes after to take it seriously. Part of the genius of the question is its simplicity. It does not require advanced mathematics to feel its weight. Anyone who has looked up at a starry night sky and felt the immensity of the cosmos has, in some way, felt the question themselves. The silence is something we can almost hear. The silence is something we can almost listen to if we listen carefully enough. Tonight, as we sit with the question, we are joining a long, quiet tradition. Physicists at lunch, astronomers at telescopes, philosophers in study rooms, children on summer porches, sleepers wondering, all of us looking up in our own way at the same patient cosmic dark, asking the same patient question. The question belongs to no one and to all of us at once. Now, gently, we will move from the historical origin of the question to the first careful attempt to put numbers on it, the Drake equation, developed a decade after Fermi's lunch, which gave scientists a framework for thinking about cosmic civilizations. In 1961, a young American astronomer named Frank Drake organized the first scientific meeting devoted to the question of extraterrestrial life. The meeting was held at the National Radio Astronomy Observatory in Green Bank, West Virginia. To organize the conversation, Drake wrote a simple equation on the blackboard. It was meant as an agenda, a way of breaking the question into pieces. It became one of the most famous equations in modern science. The Drake equation tries to estimate the number of civilizations in our galaxy that we might be able to communicate with. It multiplies together a series of factors: the number of stars that form each year, the fraction of those stars that have planets, the number of planets per star that could support life, the fraction of those planets where life actually appears, the fraction of life that becomes intelligent, the fraction of intelligence that becomes technological, and the length of time those civilizations last. Each factor is itself a deep question. How many stars form? Astronomers can estimate this fairly well. How many of them have planets? In Drake's time, this was unknown today. Thanks to telescopes like Kepler and TESS, we know it is nearly all of them. The fraction of those planets in habitable zones where liquid water could exist on the surface is also reasonably well constrained. We are slowly filling in the early terms, but the later terms are much harder. How often does life actually arise on a habitable planet? We have only one example, Earth. We do not yet know whether life appears easily or rarely. How often does life evolve to intelligence? We do not know how often does intelligence develop technology that can communicate across space. We do not know. How long does such a civilization last? We have no idea, although our own short history is a quiet warning. Because so many of the terms are uncertain, the Drake equation does not give a single answer. Instead, it gives a range of answers depending on what values you choose. Optimistic values produce estimates of tens of thousands of communicating civilizations in our galaxy. Pessimistic values produce estimates near one, just us. The equation does not solve the Fermi paradox. It just helps us see where our uncertainty lies. Drake himself was modestly optimistic. His original calculation produced an estimate of about 10,000 technological civilizations in the Milky Way. If that estimate were correct, then on average there should be a communicating civilization within roughly a few hundred light years of Earth. We have not detected any. This is part of what makes the silence so puzzling. The most uncertain term in the Drake equation is usually considered to be the lifetime of a technological civilization. If civilizations typically last only a few hundred years before destroying themselves, then most of the universe would be empty of communicators at any given moment. If civilizations typically last millions of years, the universe should be loud with their voices. The difference is enormous. The equation also depends sensitively on the fraction of life that becomes intelligent. On Earth, life began at least 3.5 billion years ago. Intelligent life arose only in the last few 100,000 years. Most of life's history was microbial. If most other worlds with life follow a similar pattern, intelligence may be much rarer than mere biology. Refinements to the Drake equation have been proposed over the years. Some authors have added factors for the fraction of intelligent civilizations that develop interstellar travel, or the fraction that choose to communicate at all. Others have proposed mathematical reformulations that handle uncertainty more rigorously. The equation has evolved, but its essential structure remains a useful tool. One important use of the Drake equation is that it shows us where to focus our research. If we want better estimates of how many civilizations exist, we need to better understand each term. We need to know how often planets form in habitable zones. We need to know how easily life arises. We need to understand the steps from simple life to intelligence. Each scientific advance tightens our cosmic estimate. The Drake equation is often presented in popular accounts as if it could give a definite answer. It cannot. It is better understood as a way of organizing our ignorance. By making our uncertainties explicit, the equation invites us to seek out the answers we lack and to be honest about the answers we do not yet have. That is its real gift. There is also a kind of poetry in the Drake equation. It is a small set of symbols that, if filled in, would tell us how alone we are. It is a chain of careful thoughts running from the formation of stars to the rise and fall of civilizations. Looking at it written out, one feels the strange responsibility of being a species that asks such questions at all. Drake himself continued working on questions of extraterrestrial life for the rest of his career. He helped lead some of the first attempts to listen to nearby stars for radio signals. He helped craft the famous Arecibo message sent toward the globular cluster M13 in 1974. He passed away in 2022 at the age of 92. His equation lives on, a quiet legacy on every blackboard. Tonight, the equation hangs in the cosmic dark above us, with most of its terms still unfilled. We are still working on them. With each new exoplanet discovered, each chemical breakthrough about the origins of life, each year that our own civilization continues to exist, we are slowly filling in the patient mathematical poem that Drake first wrote on a board in 1961. Now, gently, we will look more closely at the first few terms of the equation. How many stars there are, how many of them have planets, and how many of those planets might be suitable for life. To estimate how common life might be in the cosmos, we must first count the places where life could exist. The Milky Way galaxy alone contains roughly 300 billion stars. Across the observable universe, there are 2 trillion galaxies, each containing billions or trillions of stars. The total number is so large that the human mind cannot really hold it. There is no shortage of cosmic real estate. Not all of these stars are equally suited to host life. Some stars are too massive and short-lived. They burn out in only a few million years, far too quickly for life to evolve. Others are unstable, flaring violently and bathing nearby planets in lethal radiation. The most promising stars are calm, long-lived, middle-sized stars, much like our own sun. Smaller red dwarf stars, which make up about 70% of all stars in the galaxy, are particularly interesting. They live for trillions of years, far longer than the current age of the universe. If life can evolve around red dwarfs, then most habitable real estate in the cosmos has barely begun its history. But red dwarfs flare violently when young, and that complicates the picture. In addition to the type of star, we must consider where the star is located in the galaxy. The center of the galaxy is dense and chaotic, with frequent radiation events. The outer edges are starved of heavy elements needed to form rocky planets. Between them lies a band sometimes called the galactic habitable zone, where conditions are most stable for the slow, patient development of life. Within that galactic habitable zone, we must then look for stars with planets. For most of human history, this was guesswork. Other planets might exist, or they might not. Then, in 1992, the first planet outside our solar system was confirmed. By the early 2000s, dozens of exoplanets had been found. Today, more than 5,000 confirmed exoplanets are known. The Kepler Space Telescope, launched in 2009, transformed our understanding. By staring at one patch of sky for years, it detected the tiny dimming caused when a planet passed in front of its star. From Kepler's data, astronomers estimated that on average each star in the Milky Way has at least one planet. Many have several. The galaxy is full of worlds. Among those worlds, Astronomers are particularly interested in rocky planets that orbit within the habitable zone of their stars. The habitable zone is the region where liquid water could exist on a planet's surface, given the right atmosphere. It is sometimes called the Goldilocks zone, not too hot, not too cold, but just right. Such planets are now believed to be common. Current estimates suggest that roughly 1 in 5 Sun-like stars has a rocky planet in its habitable zone. With 300 billion stars in our galaxy, that suggests there could be tens of billions of potentially habitable worlds in the Milky Way alone. The nearest one might be only a few light years away. The galaxy is, by every count, abundant in places where life could exist. Having a rocky planet in the habitable zone is not the same as having a planet that actually supports life. A planet needs the right atmosphere, the right mass, the right magnetic field, the right amount of water, and many other conditions. Even small variations can make a planet uninhabitable, but the basic raw material, rocky worlds in temperate orbits, is plentiful. Some of the most fascinating discoveries are of planetary systems very different from our own. Some stars have hot gas giants whipping around them in just a few days. Some have tightly packed systems of small rocky worlds. Some have planets in stretched elliptical orbits that swing between freezing and boiling. The variety is enormous. Our own solar system is just one possibility. There are also moons to consider. Around the gas giants of our own solar system, several moons may have liquid water under their icy surfaces. Europa around Jupiter and Enceladus around Saturn are particular favorites. If habitable conditions can exist on moons as well as on planets, the count of potentially habitable worlds in the cosmos grows even larger. Looking beyond our galaxy, every other galaxy in the observable universe presumably contains a similar abundance of stars and planets. The total number of potentially habitable worlds in the universe is therefore an unimaginably large number. Even if life is rare, the cosmos has enormous capacity to produce it many, many times over. Of course, we have not yet directly observed any inhabited world beyond our own. Detecting life around a distant exoplanet is extraordinarily difficult. We are now beginning to study the atmospheres of nearby exoplanets, looking for chemical signatures that life might produce. The James Webb Space Telescope has begun this work. We are at the very edge of being able to ask the question directly. The simple answer to the question of how many places life could exist is that we do not know exactly, but the number is enormous. The cosmos has provided countless calm stars, countless rocky planets, countless temperate orbits, and countless icy moons. Whether life uses all this real estate or only a small fraction of it is one of the deepest unanswered questions of our time. Now, gently, we will consider the opposite possibility. Perhaps the chain of conditions needed for a planet to support life, and especially intelligent life, is much rarer than it appears. This idea is called the rare Earth hypothesis, and it is one of the more sobering proposed answers to the Fermi paradox. The rare Earth hypothesis was proposed formally in 2000 by paleontologist Peter Ward and astronomer Donald Brownlee. Their idea is that although simple microbial life may be common in the universe, the specific conditions needed for complex animal life, and especially intelligent life, are extraordinarily rare. Earth, in their view, may be one of very few worlds where everything came together. Their argument rests on a long list of conditions that Earth happens to enjoy. Earth has a stable orbit in the habitable zone of a calm middle-aged star. Earth has a moon large enough to stabilize its axial tilt over billions of years. Earth has plate tectonics which recycle nutrients and regulate climate. Earth has a strong magnetic field which protects its atmosphere from the solar wind. Each of these may be rare on its own. Earth is also located in a quiet, sparsely populated part of the Milky Way galaxy. Closer to the galactic center, supernovas and gamma-ray bursts are more frequent and could sterilize a planet's surface every few million years. Earth's location away from the dense, crowded core gives life a chance to develop slowly without being repeatedly wiped out. The presence of Jupiter, a large gas giant in the outer solar system, has also helped Earth. Jupiter's gravity has deflected many comets and asteroids that might otherwise have struck Earth, causing repeated mass extinctions. Without a friendly large gas giant in the right place, life might be repeatedly hammered back to its simplest forms. Most planetary systems lack this arrangement. The Earth-Moon system is also unusual. The Moon is large compared to Earth, much larger than typical moons relative to their planets. The Moon's gravity stabilizes Earth's axial tilt, preventing wild swings that would cause extreme climate shifts. Most rocky planets are believed to have smaller moons or none at all, leading to less stable climates over geological time. Plate tectonics, the slow movement of Earth's crustal plates, has played a crucial role in the development of complex life. It regulates the carbon cycle, helps maintain stable temperatures over billions of years, and exposes new minerals at the surface that life can use. Most rocky planets are believed to lack plate tectonics. They become geologically inactive once their internal heat is gone. Earth also has a strong global magnetic field generated by the convection of its molten iron core. This field shields the surface from the most dangerous radiation of the solar wind. Without it, the atmosphere would slowly be stripped away, and surface life would be repeatedly bathed in harmful particles. Mars lost its magnetic field long ago and lost much of its atmosphere as a result. Earth's history of complex life also depended on a series of evolutionary breakthroughs that may not be common. The emergence of complex cells from simpler ones, the eukaryotic transition, apparently happened only once on Earth and took more than 1 billion years. Multicellular life arose at least independently several times, but very slowly. The path from microbes to humans was neither short nor inevitable. Each of these factors taken alone might not be unusual, but multiplied together, they become rare. The rare Earth argument is that the joint probability of all these conditions being satisfied around any given star is very small. Even with hundreds of billions of stars, the number of worlds where complex animal life can develop might be modest, and the number with technological civilizations might be tiny. Critics of the rare Earth hypothesis point out that we are only one example. We do not yet know how Earth-like a planet really needs to be in order to host complex life. Perhaps life can flourish under conditions quite different from those of Earth. The cosmos may be more flexible than the hypothesis assumes. Until we have other examples to compare, we cannot be sure. There's also debate about whether the conditions Ward and Brownlee list are truly necessary, or whether life could find alternatives. Could life evolve without plate tectonics? Could it survive on a planet without a stabilizing moon? Could it use chemistries we have not yet imagined? These are open questions. Each may have a different answer. Even if the rare Earth hypothesis is partially correct, it does not make life elsewhere impossible. It just makes complex animal life and intelligence less common. There could be a galaxy full of microbial worlds with only a handful of complex biospheres and only a small handful of technological civilizations. The Fermi silence could simply be the silence of being one of very few minds in the dark. The rare Earth hypothesis has emotional weight as well as intellectual weight. If true, it suggests that Earth and the life on it are precious in a way our cultural traditions have long suspected. Each ecosystem, each species, each living creature represents a chain of cosmic improbabilities that may not be repeated anywhere else. The hypothesis casts a gentle light on the value of what we have. Tonight, whether or not the rare Earth hypothesis turns out to be true, it is worth holding gently in mind. Each forest, each river, each flock of birds, each sleeping child, all of them represent an unbroken chain stretching back through hundreds of conditions that had to be met for them to exist at all. They may be common in the cosmos. They may be unique. Either way, they are quietly extraordinary. Now, gently, we will look at a related but distinct idea, the Great Filter. The Great Filter is the idea that there is some difficult step somewhere along the path from non-life to interstellar civilization that most worlds fail to pass. Whether that filter lies behind us or ahead of us is one of the most important questions our species can ask. The Great Filter is a concept proposed by the economist Robin Hanson in 1996. It is a way of thinking about why we do not see other civilizations. The idea is simple. Somewhere along the long path from lifeless chemistry to interstellar civilization, there must be at least one step that is extremely difficult, so difficult that almost no one passes through it. That difficult step is called the Great Filter. The path from non-life to interstellar civilization has many steps. Habitable planets must form. Simple chemistry must give rise to self-replicating molecules. Those molecules must develop into cells. Cells must develop into complex multicellular organisms. Those organisms must develop into intelligent beings. Intelligent beings must develop technology. Technology must spread to other star systems. Each of these steps is difficult. Most worlds, the argument says, fail one of them. The question we cannot yet answer is, which step is the hardest one? Is the Great Filter behind us? In some step we already passed, or is the Great Filter ahead of us? In some step we have not yet reached. The two possibilities have very different implications for our own future. They are sometimes called the optimistic and pessimistic versions of the Great Filter hypothesis. If the Great Filter is behind us, it means we have already passed the rare and difficult step. Perhaps it was the origin of life itself, which on Earth happened only once. Perhaps it was the emergence of complex cells, which apparently happened only once in 4 billion years. Perhaps it was the development of intelligence. If so, we are extraordinarily lucky to be here, and the cosmos beyond us is mostly silent because almost nothing else has made it this far. If the great filter is ahead of us, it means the rare and difficult step is one we have not yet faced. Perhaps technological civilizations always destroy themselves through nuclear war, ecological collapse, or some other catastrophe. Perhaps interstellar travel is genuinely impossible, and so no one ever spreads beyond their home system. If the filter is ahead of us, our future is dark, and most civilizations like ours are destined to fail. Which scenario is more likely depends partly on what we find when we search for life elsewhere. If we discover microbial life on Mars, for example, that would slightly increase the probability that the filter is ahead of us. If life arose twice in our small solar system, then simple life must be common, and the filter cannot be the origin of life. The filter must lie somewhere later. That could be a sobering discovery. Some philosophers have argued that, in some sense, we should hope to find no other life when we search. Each empty world we discover reinforces the possibility that the filter is behind us. Each inhabited world we discover makes the filter ahead of us more likely. From this perspective, our cosmic loneliness is a sign of good news, not bad. We have already done the hard thing. Other philosophers point out that this reasoning, while elegant, is not certain. There may be many filters rather than one. Some may be behind us, some may be ahead of us. The hard step may be different for different kinds of civilizations. Our patient situation may be more nuanced than a single decisive threshold. If there are multiple filters, then which ones are most worth worrying about? Candidates for ones already passed include the origin of life, the origin of complex cells, the rise of intelligence, and the development of technology that does not destroy its creators. Candidates for ones still ahead include the development of long-term sustainable civilization, the avoidance of self-destruction, and the achievement of interstellar travel. The Great Filter framework has been criticized for being too simple. Real cosmic history is messy, and reducing it to a single choke point may obscure as much as it reveals, but the framework remains useful because it focuses attention on the question of where exactly the rarity in our cosmic situation lies. Whether the rarity is at the start, the middle, or the end of the path makes an enormous difference. One useful way to think about the Great Filter is to consider what we have learned about our own history. Life on Earth began very quickly after the planet cooled, within perhaps a few 100 million years. This suggests that the origin of simple life may not be the filter. On the other hand, complex multicellular life took billions of years and may have happened only once. That step is a candidate for being the filter. Another candidate is the emergence of intelligence itself. Many species on Earth have been complex without ever becoming intelligent in the sense we mean. Dinosaurs ruled the planet for more than 100 million years and did not develop technology. Whales and octopuses are highly intelligent, but do not use fire or build computers. Intelligence of the humankind may be a rare path even among complex organisms. Whether the filter is behind us or ahead of us, the framework itself is a useful reminder to take our own civilization seriously. We are at a moment in cosmic history when the question of our long-term survival is genuinely open. The choices we make over the coming centuries may decide whether we pass through the filter or not. This is true regardless of what other civilizations have done. Tonight, The question of the great filter hangs gently in the cosmic dark. We do not know where it lies. We do not know whether we have already passed through it or whether it is still ahead. We can only continue patiently, improving our science, caring for our world, and waiting to learn more about the cosmos beyond us. The answer may come slowly. It may come from a single empty Mars sample or from a single faint cosmic signal. Now, gently, we will turn toward one of the darker possibilities. What if the great filter is ahead of us? And what if it is the tendency of intelligent civilizations to destroy themselves? This sobering hypothesis is worth considering carefully. One of the most discussed possible answers to the Fermi paradox is the idea that technological civilizations tend to destroy themselves. The reasoning is sobering. As a civilization develops powerful technology, it gains the capacity to do enormous damage. If that capacity is not matched by wisdom, the civilization may use its technology to end itself, whether through war, environmental collapse, or unforeseen accidents. Our own short history with technology gives us some reason to worry. We discovered nuclear weapons in the 1940s. Within years, we had built enough to threaten our entire species. We have since discovered other technologies, biological, chemical, computational, that could potentially be even more dangerous. We have managed not to destroy ourselves so far, but our patient civilization is only about 80 years into the nuclear age. If our experience is typical, then most civilizations may face a similar narrow window between the development of powerful technology and the development of wisdom sufficient to use it. If the window is too narrow, civilizations may routinely fail. The cosmos could be full of the radioactive ruins of civilizations that did not make it through their own technological adolescence. The risks include not only deliberate war, but also accidental release of dangerous technologies. A laboratory accident with engineered organisms, a runaway artificial intelligence, an unexpected interaction between many small technologies. The number of ways a civilization can hurt itself grows with its capability. Civilizations must develop not only power, but the careful management of power. There is also the risk of slow self-destruction through environmental damage. If a civilization extracts and consumes resources faster than its planet can replenish them, it may eventually exhaust its own habitat. Climate change, biodiversity collapse, ocean acidification, all of these can degrade a planet's capacity to support its inhabitants. A slow collapse can be as final as a fast one. Some thinkers have proposed that any civilization that survives its technological adolescence must develop strong cultural norms against self-harm. They must learn to limit weapons, to share resources, to take care of their planetary home. Civilizations that do not develop these norms are filtered out. Only the careful, cooperative civilizations survive to send signals into the cosmos. This view suggests that any civilization we might one day detect would, by selection, be one that has solved its self-destruction problem. They would be civilizations that have built lasting peace, that have learned to live within planetary limits, that have created institutions capable of stewarding powerful technology across long time. They would be much older and wiser than we are. Such a civilization, if it exists, might look back on its own past with a mixture of compassion and concern for younger civilizations like ours. They might know exactly how close we are to our own filter. They might choose to remain silent, watching in the same way a careful gardener watches a fragile seedling without disturbing it. Their silence might be a kind of wisdom we do not yet understand. The self-destruction hypothesis is sobering but not deterministic. It does not say that civilizations must destroy themselves. It only says that the path through powerful technology is dangerous and that many civilizations may fail at it. Our own future is not yet written. We could be one of the civilizations that does not. The choice is partly ours. There is some evidence from human history that we have already made it through previous narrow passages. We have avoided nuclear war for decades. We have built international institutions to manage chemical weapons. We have begun to take seriously the long-term care of our planetary climate. We have, despite many failures, also achieved many quiet successes. Whether these successes will be enough for the challenges ahead is uncertain. New technologies emerge, new risks appear, the pace of change accelerates. We will need not only good fortune but ongoing care to navigate the next century. The fact that the Fermi silence might be the cosmic record of failures like the one we are trying to avoid is itself a quiet motivation to be careful. Some thinkers find the self-destruction hypothesis depressing. Others find it motivating. If many civilizations have failed, then our success is not guaranteed and we must work for it. If our work matters, then our small civilization has a chance to be one of the rare successes. The cosmic silence becomes a quiet call to take ourselves seriously. The hypothesis also reminds us that intelligence is not the same as wisdom. A civilization can be very intelligent, capable of inventing nuclear weapons, of editing genes, of building artificial minds without being very wise. Wisdom is a slower, more patient kind of capacity. It is the capacity to use power well, to think over long horizons, to care for what cannot defend itself. Civilizations need both. Tonight, the question of whether our civilization will pass through its own filter or not is genuinely open. The patient cosmos beyond us is silent. We do not yet know if that silence is the record of failures or simply the quiet of a sparsely populated cosmos. Either way, our work continues. We continue to build, to learn, to take care, to hope. Now, gently, we will turn toward more optimistic answers to the Fermi paradox. What if the universe is full of life and civilizations, but they have chosen not to make contact with younger civilizations like ours? This is the zoo hypothesis. The zoo hypothesis is one of the gentler answers to the Fermi paradox. It was proposed in 1973 by the astronomer John Ball. The idea is simple. Perhaps the galaxy is indeed full of intelligent civilizations, but those civilizations have decided to leave young, developing worlds like ours alone. We are being kept in something like a cosmic nature preserve. Under this hypothesis, the lack of contact is not accidental. It is deliberate. The advanced civilizations of the galaxy, or perhaps a single coordinating one, have agreed not to interfere with younger civilizations as they develop. The reasoning might be ethical, scientific, or practical. They might want us to develop naturally without contamination from outside influence. There are good reasons why advanced civilizations might choose this approach. Contact between a more advanced and a less advanced civilization is historically traumatic. On Earth, when ancient civilizations met more technologically advanced ones, the less advanced civilization often did not survive intact. Diseases, cultural disruption, and political subjugation took their toll. A wise galactic civilization might want to avoid causing such damage. There are also scientific reasons. Civilizations developing on their own might give us valuable data about the variety of possible paths intelligence can take. By not interfering, advanced civilizations might be preserving a kind of natural experiment. Each developing civilization is a unique opportunity to observe how intelligence and culture unfold. Interference would compromise the experiment. The zoo hypothesis also fits well with the idea of long civilizations. A civilization that has lasted millions of years has had time to develop deep ethical traditions. Such a civilization might value patient observation over hasty contact. They might wait perhaps for thousands or millions of years before initiating any communication with a developing species like our own. Under the zoo hypothesis, our cosmic neighbors might be watching us right now, gently and at a distance. They might know more about us than we know about ourselves. They might be waiting for some specific signal, perhaps a sign of cultural maturity, perhaps a sign of technological sophistication that would indicate we are ready to be contacted. The waiting could be very long. A related idea is sometimes called the interdict hypothesis. Under this version, there is an active prohibition against contacting developing civilizations. The reasoning is that contact would harm the developing civilization, so an ethical galactic community formally forbids it. Any civilization that violated the prohibition would face consequences from the others. Critics of the zoo hypothesis point out a weakness. For the hypothesis to work, every advanced civilization in the galaxy would need to participate in the restraint. Even one civilization that decided to make contact or to leave artifacts or to broadcast signals would break the silence. Maintaining perfect cosmic restraint across thousands or millions of civilizations seems difficult. Supporters reply that there might be only a few advanced civilizations, all of whom find restraint beneficial, or that the restraint is enforced somehow, perhaps by the oldest civilization in the galaxy, or that the restraint emerges naturally from the kind of long-term thinking that allows civilizations to last. The cosmic silence becomes a side effect of cosmic maturity. The zoo hypothesis has a comforting quality. It allows us to imagine a cosmos that is not empty but kindly. The silence around us would be the silence of patient gardeners watching their garden, not the silence of an empty room. We are not alone. We are simply not yet considered ready for the conversation. The hypothesis also has implications for how we should think about our own search for life. If the advanced civilizations are deliberately hiding, then ordinary searches for radio signals or visible megastructures might fail by design. The advanced civilizations might be using technologies we cannot detect. Their cosmic infrastructure might be deliberately invisible to younger civilizations like us. Some thinkers have suggested that the zoo hypothesis predicts a sudden moment of contact when a civilization reaches some threshold of maturity, perhaps when humanity develops sustainable interstellar capability or solves its self-destruction problem. The silence will break. We will all at once become aware that the cosmos has been waiting for us. the thought is gentle. Other versions of the hypothesis are less hopeful. Some suggest that we might be hidden not for our protection, but because the cosmic community considers us irrelevant. They might simply not bother. They might have evolved into forms of intelligence so different from ours that we are not interesting to them. Their silence would be neither kind nor cruel, just disinterest. Tonight, whether or not the zoo hypothesis is true, it is gentle to consider. It allows us to imagine that the cosmic dark might hold quiet companions rather than empty space. Whether they are watching kindly or ignoring us peacefully, the possibility of presence is comforting to hold. We are perhaps not alone. We are perhaps only quiet. Now, gently, we will turn toward a much darker version of the same general idea. What if civilizations choose silence not out of kindness but out of fear? This is the dark forest theory. The dark forest theory was popularized by the Chinese science fiction writer Liu Cixin in his three-body problem trilogy. The image is haunting. The cosmos in this view is a vast, dark forest. Every civilization is a hunter who walks the forest carefully and quietly. Whoever makes noise, whoever reveals their location becomes a target. The wisest civilizations stay silent and hidden. The reasoning is grim but rigorous. Suppose there are many civilizations in the cosmos. Communication between them is slow due to the speed of light. They cannot easily judge each other's intentions across such distances. If even one civilization is hostile, it could pose an existential threat. The safest strategy is to assume hostility and avoid being noticed. The dark forest theory makes two main assumptions. First, that all civilizations seek to survive. Second, that resources and territory are limited even across cosmic scales. Given these assumptions, civilizations come into competition for the same cosmic resources. Any civilization that reveals itself risks attracting unwanted attention from civilizations that might wish to eliminate competitors. The cost of attacking is much lower than the cost of being attacked. A civilization can destroy another from many light years away with relativistic weapons or self-replicating probes. The defender has no warning, no chance to react. The attacker risks only the small cost of launching weapons. In this asymmetric situation, attacking first becomes the rational choice for any civilization that fears competition. If this logic is widely understood across the cosmos, then every civilization independently arrives at the same conclusion. The best strategy is to remain silent, hidden, and to attack any other civilization that becomes detectable. The cosmos, in this view, is a graveyard for civilizations that announce themselves, and a refuge for those wise enough to stay quiet. The dark forest theory is unsettling. It implies that our own efforts to broadcast our presence through radio, through deliberately transmitted messages like the Arecibo signal of 1974, might be dangerous. We might be drawing attention to ourselves in a forest full of hidden predators. Some thinkers have argued seriously against sending any further signals. Critics of the dark forest theory point out that it depends on specific assumptions about civilizational psychology and behavior. Civilizations might not be uniformly hostile. They might develop cooperation rather than competition. Resources might be abundant enough that attack is not necessary. The theory assumes a particular game theoretic framing that may not apply universally. Even if some civilizations are hostile, others might not be. A galaxy with many civilizations might have a mix of strategies, some hidden, some open, some cooperative, some predatory. The dark forest scenario assumes that the worst strategy dominates, but this is not the only possible outcome. Cooperation can stabilize too, given time and shared interest. There are also questions about whether interstellar attack is really as easy as the theory suggests. Detecting a small civilization across light years would require enormous resources. Launching effective weapons across such distances is itself extraordinarily difficult. The asymmetry between attacker and defender might be smaller than the theory assumed. The dark forest theory has nevertheless influenced how some thinkers approach the question of broadcasting our presence. The principle of cosmic caution suggests that we should listen before speaking, learn before announcing. Even if the dark forest scenario is unlikely, the cost of being wrong could be catastrophic. Patience seems wise. The theory also illuminates a possible reason for the silence we hear. If most civilizations have adopted dark forest strategies, then most cosmic radio dials should be empty. Civilizations would communicate, if at all, on very tight beams to specific destinations, not in broad announcements that anyone could detect. Our broadband searches would naturally pick up nothing. Some thinkers have suggested that the dark forest might break down over very long times. As civilizations age and develop deeper understanding, they might transcend the competitive logic. They might find ways to cooperate across vast distances. They might create cosmic institutions for managing relations among civilizations. The dark forest might be a phase, not a permanent state. Whether or not the dark forest theory accurately describes the cosmos, it offers a useful frame for thinking about our own situation. We are a young civilization that has, perhaps imprudently, announced ourselves through decades of broadcast radio and television. We have done this without knowing whether anyone is listening. If the dark forest is real, we may have given ourselves away. Tonight, the dark forest sits gently beside the kinder versions of the Fermi paradox. In the cosmic dark, we do not know which version is true. We can only continue listening, thinking carefully, and being patient. Whether the cosmos is a kindly garden or a careful forest, our task tonight is simply to rest quietly within it. Now, gently, we will look at a related idea, the possibility of self-replicating probes called Berserkers that might be patrolling the galaxy looking for civilizations to silence. This is one of the darker corners of the Fermi conversation. The Berserker hypothesis was proposed by the physicist Fred Saberhagen and later developed by other thinkers. The idea is that some ancient civilization long ago built self-replicating probes designed to identify and destroy any other civilization they detected. Those probes might still be active, patrolling the galaxy, eliminating any signs of intelligent life they encounter. Self-replicating probes, sometimes called von Neumann probes after the mathematician who described their general possibility, could spread across an entire galaxy in a few million years. They land on resources, build copies of themselves, and continue. A galaxy could be saturated with such probes in a small fraction of its lifetime. Their existence would explain the silence very effectively. If even one civilization in the history of the galaxy built such probes with hostile intent, the probes might still be operating long after their original creators are gone. The probes do not need to be intelligent. They only need to follow simple rules. Detect a civilization, eliminate the civilization, continue. Such systems can persist far longer than the minds that created them. Why would any civilization build such probes? Perhaps out of fear that another civilization would destroy them first. Perhaps out of competition for resources. Perhaps out of an ideology that valued the dominance of their own kind. Or perhaps simply by accident, as an experimental project that escaped its makers. The reasons are many, and not all of them require malice. The Berserker hypothesis is a specific version of the more general idea that the silence we hear might be enforced by hostile actors. The hostile actors do not need to be currently active civilizations. They might be ancient automated systems, set in motion long ago, continuing their patient work across cosmic time. The galaxy would seem empty because anyone who appeared would be silenced. If berserkers exist, then any civilization that detects them would face a difficult choice: hide and hope to remain unnoticed. Try to destroy the probes before they can destroy you. Try to communicate with them in case they can be reasoned with. None of these options is obviously safe. The presence of berserkers would make cosmic existence inherently hazardous. Critics of the Berserker hypothesis point out that it requires several specific conditions to hold. There must have been a civilization with the technology and motivation to build such probes. The probes must have been built robustly enough to persist for millions or billions of years. They must have spread effectively across the galaxy. Any of these assumptions might fail. There is also a question of whether self-replicating probes would actually function reliably over geological time. Mechanical systems wear out. Software systems develop bugs. Replication accumulates errors. After billions of years of replication, the probes might have drifted far from their original programming, becoming something quite different from what their creators intended. The hypothesis is harder than it first appears. Despite these difficulties, the Berserker scenario is taken seriously enough that it has been used as one reason for caution about broadcasting our presence. Even if berserkers do not exist, the cost of being wrong is so severe that the question deserves careful thought. We might want to listen widely and broadcast narrowly until we know more about who else is out there. More generally, the Berserker hypothesis points to a broader concern. If there are any hostile actors in the cosmos, however arising, they could affect our chances of long-term survival. The question of whether we are alone may matter less than the question of whether the cosmos is friendly. Both are uncertain. Both deserve careful attention. There are other variants of the hostile alien hypothesis as well. Some imagine that advanced civilizations periodically engage in cosmic warfare with one another. Others imagine that a single dominant civilization controls large parts of the galaxy, allowing some kinds of life to develop and not others. The variations are many, and most are speculative. The hostile scenarios share a common feature. They explain the silence by saying that what we do not see is not what is absent. The silence we hear is the silence of careful prey, or the silence of conquered territories, or the silence of patient predators. The The cosmos is loud with cosmic activity that does not reach us by design, by intent, or by indifference. Most thinkers consider the hostile scenarios less likely than the gentler alternatives. Cooperation, in many simulations and historical analogues, tends to outcompete pure hostility over long times. Civilizations that survive long are usually those that have learned to cooperate, not to dominate. The cosmic dark might therefore be more friendly than the hostile scenarios suggest. But uncertainty remains. Tonight, the patient, darker possibilities sit gently beside the patient, gentler possibilities. We do not know which is true. We can only continue our small, careful work, watching the cosmic dark with patient attention, listening with patient care, and being mindful about what we ourselves announce into the silence. The questions are large. The answers will come slowly, if at all. Now, gently, we will set aside the more speculative possibilities and consider a more practical question. How hard is interstellar travel really? Could it explain the silence simply by being too difficult for any civilization to achieve? One straightforward answer to the Fermi paradox is that interstellar travel might simply be too difficult for any civilization to achieve at large scales. The cosmos is enormous. The distances between stars are so great that even the most advanced civilizations might find it impractical to send themselves or their machines across them. The silence might be the silence of the great cosmic distances themselves. The nearest star to our Sun is Alpha Centauri, about 4¼ light years away. Light, the fastest thing in the universe, takes more than 4 years to make the trip. Our fastest current spacecraft would take tens of thousands of years to reach it. Even with significant technological improvements, the journey would take generations of travelers. Most stars in the galaxy are much farther away than Alpha Centauri. The center of our galaxy is 26,000 light years from us. Other galaxies are millions or billions of light years away. To explore a meaningful fraction of the cosmos would require enormous patience and enormous resources. Many thinkers have argued that the cost simply does not make sense for any civilization. The physics of interstellar travel is harsh. To travel at a significant fraction of the speed of light requires enormous energy. A spacecraft accelerating to 10% of light speed would need fuel equivalent to many planets. Accelerating further requires exponentially more energy. The speed of light itself is a hard limit imposed by the laws of physics. No shortcut around it has ever been found. Even at high speeds, the journey times remain long. At 10% of light speed, the trip to Alpha Centauri takes more than 40 years. At 1%, it takes more than 400 years. The civilizations choosing to send their members across such distances must build sustainable generation ships, or solve the problem of suspended animation, or find some other way of preserving life across the journey. There are other risks. At high speeds, a single grain of interstellar dust becomes a powerful weapon striking the spacecraft. Cosmic radiation accumulates over time. Mechanical systems must work reliably for centuries. Crew populations must remain genetically and socially healthy over many generations. Every interstellar mission must solve a long list of difficult engineering and biological problems. Some have proposed alternatives. Instead of sending biological beings, civilizations might send small robotic probes, much easier to build and to accelerate. Some have proposed sending the information needed to reconstruct a civilization at the destination rather than the physical beings themselves. Some have proposed gathering raw materials and building new spacecraft at each stopover point. Even with robotic probes, the spread across a galaxy takes a long time. A probe traveling at 10% of light speed, replicating at each new system, can fill the galaxy in about 10 million years. That sounds fast on cosmic scales, but it still requires that some civilization has been around long enough and committed enough to start the process and let it run. Some thinkers argue that interstellar exploration may simply not be worth the cost for most civilizations. A civilization could meet most of its needs within its home system, especially after it has learned to engineer its own environments. The motivation to spread might be weaker than we sometimes assume. Many advanced civilizations might prefer to stay home, content within their own star systems. Other thinkers point out that even if interstellar travel is hard, communication is much easier. Radio signals travel at the speed of light and require relatively little energy to produce. If civilizations exist within a few hundred light years of us, we should be able to hear them even if they cannot physically visit us. The silence in radio frequencies is therefore independent of the difficulty of travel. Of course, advanced civilizations might use forms of communication we do not yet recognize. They might use laser pulses tightly directed to specific receivers. They might use gravitational wave signaling. They might use technologies we have not yet imagined. Our patient radio searches might be looking for the wrong kinds of signals, missing the actual communications happening all around us. The difficulty of interstellar travel does explain part of the silence, but not all of it. Even if no civilization ever travels between stars, civilizations should still leave detectable signs. They should change the spectra of their stars by industrial activity. They should leak radio communications. They should build large engineering projects we can see. Their continued existence should be visible from far away. Some thinkers have proposed that advanced civilizations gradually retreat from outward expansion. They focus on improving their internal lives. They build smaller, more efficient systems. They become less visible over time rather than more visible. Their cosmic presence becomes a quiet inward turn rather than a loud outward spread. The cosmos would then naturally fall quiet as civilizations mature. Tonight, the difficulty of interstellar travel sits gently beside the other partial answers. It is real, it is significant, it is not by itself a complete explanation. The cosmos is vast, and crossing that vastness is hard. But the silence we hear is not only the silence of unspanned distance, it is also the silence of something we still do not understand. Now, gently, we will look at how we have actually searched the cosmos for signals of other civilizations, the long, patient work of SETI, the search for extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, is the long, patient effort to detect signs of other civilizations by listening to the cosmic radio sky. The work began in 1960 when Frank Drake pointed an 85-foot radio telescope at two nearby sun-like stars and listened for any sign of artificial signals. He heard nothing definite, but he opened a door that has remained open ever since. The reasoning behind radio searches is sound. Radio waves travel at the speed of light. They pass easily through dust and gas. They can carry information over enormous distances using relatively little energy. Any technological civilization that wanted to communicate with others, or that simply leaked communications during its own activities, would almost certainly produce detectable radio signals. Drake's first search, called Project Ozma, listened for a few hundred hours and found nothing. But it established the method. Since then, many other searches have followed. The Soviet Union conducted searches in the 1960s and 70s. NASA had a program in the 1990s that was canceled before completion. The SETI Institute, founded in 1984, has continued the work continuously. Modern SETI uses sophisticated digital techniques. The Allen Telescope Array in Northern California can listen to many radio frequencies simultaneously. The Breakthrough Listen project, founded in 2015, has scanned thousands of stars across millions of frequencies. The total amount of sky and frequency space that has been searched has grown enormously, but it remains a small fraction of what is possible. Despite many decades of listening, SETI has never confirmed detection of an artificial signal from another civilization. Several promising candidates have appeared over the years, but each has turned out to be either natural in origin, terrestrial interference, or impossible to verify. The most famous candidate, the WOW signal of 1977, has never been repeated and remains unexplained. The WOW signal was detected by the Big Ear Radio Telescope at Ohio State University on August 15, 1977. It was a strong, narrow-band signal that lasted 72 seconds and then disappeared. The astronomer Jerry Eman circled the signal data on the printout and wrote, "Wow," beside it. Despite many searches since, the signal has never been detected again. It remains one of the great unsolved mysteries of SETI. Beyond traditional radio searches, modern SETI also looks for optical signals. Some civilizations might choose to communicate using laser pulses rather than radio waves. Laser pulses can be focused tightly and can carry enormous amounts of information. Several searches now scan the sky for unusual flashes of light that might be artificial. None has been confirmed, but the searches continue. There are also searches for signs of technology rather than signs of communication. Some astronomers look for unusual infrared emissions that might indicate large engineered structures around stars. Others look for chemical signatures in exoplanet atmospheres that could only be produced by industrial activity. The hunt for technosignatures is a growing field, distinct from but related to the search for intentional signals. SETI has had to deal with practical challenges. Funding has often been limited. Telescope time has been hard to obtain. Many scientists have considered the work speculative. Despite these challenges, the work has continued, supported in recent years by private donors and crowdfunding, as well as by some government agencies. The patient listening goes on. The data from SETI searches is itself a kind of negative result. The fact that we have not heard any clear signal tells us something. It tells us that nearby sun-like stars are not home to civilizations broadcasting strong signals on the frequencies we have searched. It tells us that the immediate neighborhood of our galaxy is, by current evidence, radio quiet. Of course, the negative result is partial. We have searched only a small fraction of all stars, only a small fraction of all frequencies, and only for short total durations at each. The cosmos could be full of civilizations broadcasting on frequencies we have not yet checked, or on schedules we have not yet caught. The patient listening must continue and grow and improve. Some thinkers have argued that we should not only listen, but also broadcast. Active SETI, also called METI, sends deliberate messages toward nearby stars in the hope that someone will respond. The Arecibo message of 1974 was an early example. Other transmissions have been made since. The practice remains controversial because of the concerns we discussed earlier about cosmic safety. The work of SETI is patient work. Most days produce no result. Most years produce no result. The reward, if it ever comes, will be one of the most important discoveries in the history of science. Until then, the work continues by faith. Faith that the listening matters, that the cosmos has something to say, and that our patient ears might one day catch the first whisper. Tonight, somewhere on Earth, radio telescopes are still pointed at quiet stars, recording carefully, listening patiently for any whisper from the cosmic dark. They have done this for 60 years. They will continue for 60 years more. The listening itself is a kind of prayer the species has made to itself, a quiet hope that we are not alone, and a quiet willingness to wait as long as needed. Now, gently, we will look more specifically at where we have already searched, and what kinds of objects in the sky we have studied closely for signs of others. Over the past 60 years, we have searched many specific places in the cosmos for signs of other civilizations. The work has been patient and selective. We have focused on the most promising targets first: nearby sun-like stars, stars with known planets in their habitable zones, and stars in regions of the galaxy where life seems most plausible. The closest stars to Earth are obvious first targets. Alpha Centauri, just over 4 light-years away, has been searched many times. Proxima Centauri b, an Earth-sized planet in the habitable zone of its small red dwarf star, has received particular attention. So has Barnard's star, Wolf 359, Lalande 21185, and Sirius. None has produced a confirmed signal. In 1977, the famous Voyager Golden Records were launched aboard the Voyager spacecraft. These records carry images and sounds from Earth, intended as a greeting to any civilization that might one day encounter them. The Voyagers have now left the solar system and are drifting slowly through interstellar space. They will likely never be found, but the gesture itself was meaningful. In 1974, the Arecibo message was transmitted from Puerto Rico toward the globular cluster M13, 25,000 light-years away. The message was a short-coded greeting describing humans, our solar system, and our basic chemistry. It will take 25,000 years to reach its destination. By the time any response could return, our civilization will likely be very different or gone. Several thousand stars within a few hundred light-years have been observed for varying lengths of time. Some have been observed many times, some have been observed only briefly. The total amount of sky and frequency space surveyed remains modest compared to the total available. We have searched perhaps the equivalent of a hot tub from an entire ocean of cosmic possibility. In recent years, the Breakthrough Listen project has accelerated the pace. Funded by a private foundation, it has surveyed thousands of nearby stars in detail. The project also targets specific objects of interest, such as nearby galaxies, exotic neutron stars, and unusual events like fast radio bursts. The volume of data being collected is enormous, and the analysis is ongoing. One particularly intriguing target was the star KIC 84628552, sometimes called Tabby's star or Boyagin's star. The Kepler Space Telescope detected unusual dimming patterns in its light, which some scientists speculated might be caused by a swarm of large engineered structures around the star. After detailed study, the dimming is now believed to be caused by clouds of cosmic dust rather than structures, but the excitement was real. Searches have also been directed at distant galaxies. If an entire galaxy were inhabited by an advanced civilization, the cumulative energy use might be detectable in its infrared emissions. Several studies have looked for this kind of galactic scale signature among hundreds of thousands of galaxies. None has produced a clear positive result. In our own solar system, several searches have looked for signs of past or present visitation. We have looked at the Moon and other planets for ancient artifacts. We have searched our orbital region for unusual objects that might be probes. We have monitored the asteroid belt and the outer solar system for anomalies. Nothing definitive has been found, though the searches continue. In 2017, an unusual object called Oumuamua passed through our solar system. It was the first confirmed interstellar object ever observed. Its strange shape and unusual acceleration prompted some scientists to speculate it might be artificial, perhaps an alien probe. The mainstream view has remained that Oumuamua is most likely a natural object, perhaps an unusual comet or fragment of an asteroid. Each year, new exoplanets are discovered, and many of them become candidates for further study. The James Webb Space Telescope is now studying the atmospheres of nearby exoplanets, looking for chemical signatures that might indicate life. Future missions will improve this capability further. The hunt for biological signatures complements the hunt for technological signatures. We are also looking with new instruments at higher frequencies, including microwave and sub-millimeter wavelengths, and at lower frequencies including very long wavelength radio waves. Each frequency band opens new possibilities for what kinds of signals might be detected. The cosmos has many channels. We have only begun to scan them carefully. The cumulative result of all our searches so far is this. We have not detected anyone, but our search has been a small fraction of what is possible. The cosmic library is enormous, and we have read only a few pages. Whether the pages we have not yet read hold something or hold nothing, we cannot say. We can only continue reading patiently. Tonight, somewhere in the world, radio telescopes are aimed at quiet stars. Their patient receivers are recording data that will be analyzed in the days to come. Most of that data will turn out to be nothing. Some small fraction might be something. The work continues without certainty of reward because the question matters too much to abandon. The search itself has become a quiet tradition. Now gently, we will turn toward one of the more exotic possibilities. What if advanced civilizations build enormous structures we might be able to detect? The Dyson sphere is the classic example of such an idea. In 1960, the physicist Freeman Dyson proposed an idea that has shaped the imagination of science fiction and cosmic searching ever since. He suggested that a sufficiently advanced civilization might build a vast structure around its star, capturing all of the star's energy for its use. Such a structure, now called a Dyson sphere or Dyson swarm, would be enormous and might be detectable from across the galaxy. The idea was not originally about specifically alien civilizations. Dyson was thinking about the energy needs of an expanding technological society. He pointed out that as a civilization grows, it requires more and more energy. The total energy output of its home star is enormous compared to current human use. If a civilization wanted to grow much larger, it might surround its star to harvest more energy. A literal solid sphere around a star is mechanically impossible. The gravitational and structural stresses would be too great, but a swarm of many smaller structures, each capturing some fraction of the star's light, would be feasible. Such a swarm might be made of millions of independent solar collectors orbiting in carefully coordinated patterns. The cumulative effect would be enormous energy capture. From a distance, a star surrounded by such a swarm would appear unusual. Some of its visible light would be absorbed by the collectors. The collectors would then re-emit that energy as waste heat, which would appear as infrared radiation. The star would look dim in visible light but bright in the infrared. Such a signature might be detectable across many light years. Several searches have looked for Dyson sphere signatures. The basic approach is to find stars that show too much infrared radiation for their type. Several candidates have been examined over the decades. So far, all have turned out to be ordinary stars surrounded by clouds of natural dust or with unusual but explainable properties. No confirmed Dyson sphere has been found. If Dyson spheres or partial Dyson swarms exist, they should be detectable across galactic distances. The fact that we do not see them in our galaxy is itself a piece of evidence. Either no civilization in the Milky Way has built such a structure, or the technology produces signatures different from what we expect, or the civilizations choose not to. Each possibility has implications. Dyson spheres are only one example of cosmic megastructures that have been imagined. Some thinkers have proposed ring worlds, giant ribbons orbiting stars at habitable distances, providing enormous living space. Others have proposed shell worlds, hollow spheres around small stars or other objects. Others have proposed matryoshka brains, layered structures of computers using a star's full energy output. Other megastructure ideas include cosmic mirrors that reflect light to power distant operations, stellar engines that move stars across the galaxy over millions of years, and even attempts to harvest energy from black holes. Each of these would be detectable in principle by careful observation. None has been confirmed. The absence of obvious cosmic engineering is one of the strongest pieces of the Fermi puzzle. The astronomer Nikolai Kardashev proposed a famous classification of civilizations by their energy use. A Type I civilization uses the full energy available on its home planet. A Type II civilization uses the full energy of its home star, essentially a Dyson sphere builder. A Type III civilization uses the full energy of its home galaxy. We are currently below Type I. We are perhaps 0.7 by current estimates. If most advanced civilizations are Type II or Type III, we should be able to see them. Their cosmic engineering would be unmistakable across enormous distances. The fact that we do not see them suggests either that there are no Type II or Type III civilizations in our cosmic neighborhood, or that we are looking for the wrong signatures, or that something prevents civilizations from reaching those scales. Some thinkers have proposed that advanced civilizations might not need megastructures. As technology becomes more efficient, the energy needed for any given purpose might shrink rather than grow. A civilization might achieve sophisticated existence using less energy, not more. They would then become invisible to searches that assume increasing energy use. The growth assumption itself might be wrong. Others have proposed that civilizations might transition to forms of existence we cannot recognize. They might upload themselves into computers, becoming patterns of information rather than biological beings. They might use technologies based on physics we have not yet discovered. The signatures we look for might be entirely the wrong kinds of signatures. The cosmos might be full of activity we cannot perceive. The search for megastructures continues. New instruments and new techniques may reveal subtle signatures we have missed. The Wide-Field Infrared Survey Explorer and other infrared observatories have cataloged vast numbers of stars and galaxies. The data is still being analyzed for unusual patterns. Future telescopes will improve the resolution further. We are gradually mapping the cosmic infrared sky. Tonight, in the dark sky above us, millions of stars shine quietly. If any of them is surrounded by an engineered swarm, that swarm is too small or too efficient for us to have detected. The stars look natural. The galaxies look natural. The cosmos appears to be running on the basic processes of physics, not on the deliberate engineering of intelligent minds. That observation is one of the deeper mysteries we hold. Now, gently, we will turn toward a stranger possibility. What if the cosmic silence has nothing to do with other civilizations, because the cosmos itself is not what we think? This is the simulation hypothesis. The simulation hypothesis is one of the strangest answers to the Fermi paradox. It was proposed in its modern form by the philosopher Nick Bostrom in 2003. The idea is that our entire reality might be a computer simulation run by some more advanced civilization. The silence we hear from the cosmos might be a feature of the simulation, not a fact about an underlying physical universe. Bostrom's argument relies on a careful chain of reasoning. If any civilization ever reaches a level of technological development where it can simulate conscious minds, and if such civilizations would choose to run many such simulations, then the number of simulated minds would vastly outnumber the number of original biological minds. Statistically, any given conscious being is more likely to be in a simulation than in the original reality. This is a strange conclusion. It does not mean we are definitely in a simulation. It only means that at least one of the following is true. Either civilizations like ours never reach the technological level to run such simulations, or civilizations that reach that level choose not to run them, or we are almost certainly in a simulation right now. Each of these possibilities is interesting. If the simulation hypothesis is true, the Fermi paradox becomes a puzzle inside a puzzle. The silence we hear might not reflect the actual physical universe at all. It might reflect the limits of the simulation we are in. The simulators might choose not to populate the simulated cosmos with other civilizations, either to save computational resources or for reasons we cannot guess. The hypothesis is sometimes met with skepticism. Critics point out that it depends on several assumptions about technology, computation, and consciousness that are not certain. They argue that we have no good reason to take the hypothesis seriously beyond a kind of philosophical thought experiment. Others argue that the hypothesis is essentially unfalsifiable and therefore not science. Supporters of the hypothesis reply that it makes specific predictions. If we are in a simulation, the simulators might make computational shortcuts that could, in principle, be detected. They might use discrete units of space and time. They might limit the precision of certain calculations. Some physicists have looked for such signatures. None has been confirmed, but the possibility remains. Variations of the hypothesis abound. Some thinkers propose that we are in a deliberate simulation run for some specific purpose, perhaps to study how civilizations develop, or to explore counterfactual histories, or simply for entertainment. Others propose that we are in an emergent simulation arising naturally from some underlying mathematical structure, with no conscious simulator behind it. Some philosophers have noted that ancient religious traditions also speak of a created reality made by some higher mind. The simulation hypothesis is in some ways a modern technological reformulation of older ideas about the universe being made and held by something beyond it. The frame is different, but the basic intuition is old. We have asked this question for a long time. Whatever the simulation hypothesis turns out to mean, it expands our sense of cosmic possibility. The universe might be vastly stranger than we have so far imagined. Our patient view of physics and biology and astronomy might be only a thin slice of a much deeper reality. The silence we hear might have layers of meaning beyond what we can yet perceive. Practically, the hypothesis does not change much about how we live our lives. Whether we are in an original reality or a simulated one, our experiences are real to us. The people we love are real to us. The work we do matters to us. The silence we hear is the silence we live with. The hypothesis becomes at most a quiet philosophical footnote in our daily existence. Still, the hypothesis raises ethical questions. If we run our own simulations of conscious minds, are we creating beings we have responsibilities toward? If we are simulated, do those who simulate us have responsibilities to us? The questions of moral status across simulation boundaries are entirely new, and our intuitions are not yet developed to handle them. The simulation hypothesis is often discussed alongside the Fermi paradox because both point at the same strange situation. Our cosmic dark feels stranger than we can fully describe. Whether the cosmos is empty for ordinary reasons or empty by design, or strange in ways we cannot imagine, our patient task is the same. We try to understand, we try to be careful, we try to live well within whatever the situation turns out to be. The hypothesis also suggests a possible reason for cosmic silence that is quite different from the others we have considered. If the simulation does not include other civilizations, we will never find them, no matter how hard we look. The silence is built into the structure of our reality. There is no failure of search. There is simply nothing to find. Tonight, the patient possibility of a deeper layer beneath our cosmos sits gently in the dark. We cannot prove it. We cannot disprove it. We can only hold it as one possibility among many, neither dismissing it nor accepting it, neither alarmed by it nor reassured. The cosmic question itself remains beneath any framework we use to consider it. Now, gently, we will move toward more grounded contemplation. Even if we are alone, even if the cosmos is empty, the long span of cosmic time itself contains its own quiet meaning. We will think about the deep time scales and the cosmic loneliness that is part of being a patient mind in a patient universe. Some answers to the Fermi paradox have less to do with where civilizations are and more to do with when they are. The cosmic time scale is enormous. The galaxy has existed for more than 13 billion years. The universe has existed for nearly 14 billion years. The age of any one civilization is brief compared to these timescales. Civilizations may rise and fall, but at any given moment, most of cosmic time finds the cosmos empty. Suppose civilizations typically last for a few thousand years before fading away by any cause. The galaxy has had time for thousands of generations of civilizations to rise and fall. But at any specific moment, the number of active civilizations might be small. They might be scattered across the long timeline, never overlapping. We might be one such brief flicker, alone for our entire history, simply because we missed the others by millions of years. This temporal loneliness is a subtle but powerful idea. Even if civilizations are common over cosmic history, they might never coexist. The light from one civilization's broadcast might take so long to reach us that by the time it arrives, the civilization itself is long gone. We might be listening to the sounds of an empty stage where many performances have already ended. There is also the question of how long any civilization might last. Our own civilization is only a few thousand years old in any complex form. Our technological civilization is only a few hundred years old. We do not know how much longer we will continue. We have only a small data point in a cosmic statistic. Other civilizations might have lasted longer or shorter. We do not yet have enough data to know. Cosmic timescales humble the question of our own civilization. The galaxy will continue for billions of years after we are gone. The universe will continue much longer than that. The stars will eventually all burn out. Black holes will eventually evaporate. The universe will eventually grow so dilute that no new structures form. Our brief moment in this enormous arc is genuinely small. And yet our brief moment is precious precisely because it is brief. The capacity to ask the question, to wonder about other minds, to feel the cosmic dark. This is a rare event in cosmic time. The universe spent billions of years arranging matter so that something could eventually wonder about the universe. We are part of that wondering. The patient cosmic process has produced us, and through us has begun to think about itself. The temporal loneliness of any civilization carries its own kind of beauty. Each civilization is a unique pattern of thoughts, feelings, and discoveries arising once and never again. The fact that civilizations do not necessarily overlap does not mean they are without meaning. Each is its own complete story, told in its own time, regardless of whether others ever hear it. There is a particular gentleness in considering that we might be one of many civilizations that have existed alone in their times. Each looked up at the patient dark, asked the same patient question, listened with the same patient hope, and found the same patient silence. None of them found the others. None of us has found the other. The shared experience of cosmic loneliness might itself be a kind of cosmic community across time. There is also a question of cosmic timing more broadly. We exist now in a particular era of cosmic history. Most of the future of the universe lies ahead, but in some ways the present moment is a special one. Star formation is still occurring. Many habitable planets still exist. The cosmic background is still cool enough for biology. We are in a relatively rich era of cosmic possibility. In the very long future, conditions for life will become harder. Stars will die, galaxies will dim. The cosmic background radiation will continue to fade. Eventually, the universe will become quiet and cold, with only the slow processes of decay and dissipation continuing. The era we are in when life can exist is itself a brief window in the deeper history of the cosmos. Our brief presence in this brief habitable era is itself a remarkable convergence of timescales. We are here in a cosmic moment when stars still burn brightly, when planets still form, when chemistry still produces the rich variety of life. We are not just lucky to exist as ourselves, we are lucky to exist now in this particular phase of the cosmic story. There's also a strange comfort in cosmic loneliness. We do not have to feel responsibility for the silence. The silence is not our fault. The silence is not anyone's fault. It simply is. We did not invite the silence, and we cannot make it speak. We can only sit with it patiently, the way one sits with the silence of an old friend who has not yet spoken. The patient cosmic dark contains its own kind of company. The stars are still there. The galaxies are still there. The deep, slow processes that have produced us are still ongoing. We are not in nothing. We are in something enormous, ancient, patient, and quiet. Whether that something contains other minds or not, it contains us, and it has contained the long, slow story of our arrival. Tonight, the cosmic time stretches far beyond our small moment. We are here briefly, asking the question briefly, sitting with the silence briefly. The cosmos itself has been doing this for billions of years and will continue for billions more. Our small attention to the question is, in its own way, a small contribution to the long cosmic story of asking the question. Now, gently, we will move toward a final reflection on what our silence might mean, not as a problem to solve, but as a quiet condition to live with. What does it mean for a small civilization to be alone in a vast cosmos? We have visited many possible answers to the Fermi paradox tonight. Some are gentle, some are dark, some are strange. None has been confirmed. The cosmic silence we hear continues, indifferent to our attempts to explain it. After 60 years of careful work, we know more than we did, but we are still very far from a definite answer. The question remains open. What is striking, looking back over the hypotheses, is how many different kinds of answers are possible. The silence might be because civilizations are rare. The silence might be because civilizations destroy themselves. The silence might be because civilizations choose not to contact us. The silence might be because the cosmic distances are too great. The silence might be because we are listening on the wrong channels. The silence might be because the cosmos itself is not what we think. Each of these possibilities has implications for how we should live as a small civilization within a cosmos we do not fully understand. Some of them suggest we should be careful. We might be vulnerable to threats we have not yet noticed. Some suggest we should be precious. Our existence may be a rare achievement worth preserving. Some suggest we should be patient. The cosmic conversation might come if we wait long enough. One thing all the hypotheses have in common is this: they make our own civilization significant. Whether we are rare, threatened, precious, watched, or simply one of many across deep time, our existence matters. We are here, we are conscious, we are asking the question. Whatever the cosmic answer turns out to be, the asking itself is a remarkable thing. A few corners of the cosmos do this kind of work. The silence also gives us a certain responsibility. We are perhaps witnesses for the part of the cosmos we can perceive. We see what the stars look like. We hear what the cosmic radio sky sounds like. We measure what the cosmic background reveals. Whatever the silence means, we are the ones who have been listening to it. The cosmic record passes through us. We can choose what to do with that responsibility. We can choose to keep listening. We can choose to keep searching for life on other worlds with patient, careful eyes. We can choose to keep refining our understanding of the universe and our place in it. We can choose to care for our small planet where the cosmic story we know best is unfolding. None of these choices requires us to know the answer. Each is meaningful even in uncertainty. The silence also offers a kind of intimacy. The cosmos is enormous and indifferent. The silence between us and any other civilization, if there is one, is enormous and indifferent. And yet within that silence, we have each other. We have our families. We have our communities. We have the small but precious bonds we build during our brief time. The cosmic silence makes the close warmth of human life more vivid by contrast. There is also a strange peace in not knowing. The cosmic silence does not demand answers from us. It does not force us to choose. It simply is. We can hold it gently, like one holds an old unsolved question that one no longer expects to solve. The question becomes a quiet companion rather than an urgent problem. It teaches patience. The silence has shaped how some scientists and philosophers think about the future. If we are rare, we should try to last. If we are at risk, we should be careful. If we are precious, we should care for ourselves and for each other. The patient cosmic silence has become, in some quiet way, an argument for kindness, an argument for patience, an argument for taking the long view of our own situation. Whether or not we ever hear from another civilization, our task remains the same: to live carefully, to learn slowly, to build well, to care for the small precious island of life we have inherited. The cosmic question may never be answered in our lifetimes, or in our species' lifetime, or at all. The small work we do remains worthwhile regardless of the answer. And yet there is reason for quiet hope. Our patient searches are getting better. Our telescopes are getting sharper. Our understanding of the chemistry of life is deepening. Our maps of nearby exoplanets are improving. Within a few decades, we might find clear evidence of microbial life elsewhere. Within a few centuries, we might find clear evidence of intelligence. The patient work might yet bear fruit. Even if we never find another civilization, the search itself has changed us. It has taught us to think on cosmic scales. It has taught us that our small civilization is part of something enormous. It has taught us a kind of cosmic humility and a kind of cosmic gratitude. We exist. We notice that we exist. Few things in the cosmos do that. The Fermi paradox, in the end, is less a problem to be solved than a quiet companion to live with. Like all the deepest questions, it teaches us about ourselves. The cosmic silence is a mirror in which we see dimly the outlines of who we are, small, curious, alone, or perhaps not alone, asking the question, regardless of whether we get an answer. Tonight, somewhere on Earth, a sleeper drifts into rest while the stars continue to shine quietly above. The cosmic silence continues. The patient cosmos continues. The question continues. Tomorrow we will continue too. The work of asking, of listening, of caring, of being briefly and brightly here in a vast and patient cosmos. That work is enough. Now, gently, we will bring our journey through the Fermi paradox to a soft close. The cosmic silence will continue tonight and tomorrow, and for all the nights to come. We can rest within it, gently as one rests within any deep and ancient mystery that one is not required to solve. Thank you for letting us be part of your night. If this slow journey helped your body settle, subscribing is the kindest way to keep these hours coming. Each week we travel somewhere new and ancient and unhurried, always within the quiet vastness of cosmic space and its long silence, always meant for rest. Good night. Sleep deeply. Sleep slowly. The galaxies are still drifting quietly through cosmic space tonight. Stars are still being born in distant nebulae, still slowly dying in supernova light, still cooling into red dwarfs that will outlast everything we will ever know. Somewhere, perhaps, another mind is looking up at its own sky and wondering exactly the same patient question, and the cosmic silence between us is the gentle, immense, mysterious answer we are all still trying to understand. They have been here long before you, and they will be here long after, and tonight they keep you company while you rest. Good night from the Circadian Institute. And with that, we bring tonight's quiet journey through the question of where everyone is to a soft close. The cosmic silence will continue tonight. The stars will continue to shine. The patient question will continue to be asked by minds across cosmic time. Sleep softly tonight. The cosmos is patient. Whatever it has to tell us will come gently in its own time.